Je m'appelle Kyler Chen. Today's lecture is in English, and the slides will be bilingual, but you can ask questions in French or English. Vous pouvez poser des questions en français ou en anglais. So, project motivations. Why did I make this? I really like maps. And I also am very concerned about climate change as a young person. And the dominant emission source in California, where I live, 51% of emissions in my city come from cars. And we have to drastically improve public transportation by encouraging people to take public transportation. And a lot of people discover these services now on their phones. But sometimes the travel times are 2 hours, 3 hours. And we start to ask, what if we can give people better query times? If we can say, oh, you have a bike. You can shave off. You don't have to ride this short section on a bus. You can just bike from this stop to this stop, and then if we can shave off enough time, then maybe it's more convenient for you. And so we also provide, really obsessed with trains, and so we provide a lot of stuff for rail fans, and we also work with agencies to sort of improve the public transportation experience. All right, so we'll do a very quick demo. Oh, there we go. So here is, ooh, live demo time. Let's go. So if the internet is slow, then come on. So you can see nearby departures. We do that kind of querying. We're working on routing algorithms, and then there we go. Here, and you can click on one of these, and it's querying out of our Rust RealTime Database. So here's one vehicle, and you can see that one's canceled, so you can't go to that stop there. That's a demonstration. The live demo worked this time. Oh. You see. Excellent. So the first thing that I was struggling with initially is that a lot of agencies have overlapping URLs. So MTA is a huge agency in New York, and I don't even know how to classify it as an agency. You have like Long Island Railroad, Metro North, a ton of bus services with like different bus companies inside MTA. There's the subway service, and there's also en France, there's one agency will operate this set of URLs, and another agency will operate this set of URLs. And so what I realized is we can just do like a depth first search. So we can just say this URL goes to this agency, and then this agency goes to this URL, and then we just collect all of them, and we can group them into agencies. And you can see the boundaries that we've drawn. But what in Europe, actually the agencies sort of operate, they collate data nationwide. While in North America, it's and also in Japan, we kind of do it by county and county or city by city here. So if in Europe, what we actually have to do is kind of split it closer to per box a region, or we can also do k-means clustering. It really depends on what algorithm we're choosing for that specific problem. And who of you are familiar with distributed systems here, work on Kubernetes? See a couple of hands here. Oops. So distributed systems are actually surprisingly easy in Rust. You're mainly leaning on etcd and Kubernetes, and what's really cool is that everyone's kind of done most of the work for you. You just kind of use those libraries. etcd, what we can do is that we just have a pool of servers, and you just have one of them say, I want to be the leader. And once one of them is successfully the leader, you can then assign a bunch of tasks. So let's say you have a bunch of agencies. You can then assign out those agencies to your different servers. And once those workers are assigned, then those workers can pull out the data out from the etcd database. And etcd maintains this 100% consistency because there's a RAF consensus algorithm that it uses. To be honest, I've taken the distributed systems course. It's still really complex to me, but it works, and that's enough for me. So you can access the assignments, and if you want to store data in etcd as Rust structures, it's really easy. Just use serde And you can store whatever. Maybe you store your assignments in there or some particular key. And so we spread it out by agency. That's one cool way that we can do it. So the GTFS specification was created by Google and Portland. And those two agencies, they really work together. Well, Google's a company. Initially, they worked together to form the GTFS specification. It describes, the order that the trips come in, what the routes and the colors of the routes are, and then what days those routes operate, as well as how much, each service costs. And then there's every single month, there's more proposals, there's more infighting on GitHub. I know everyone here is familiar with GitHub issues and people fighting on it. And then a couple years later, they were like, oh, we should probably add some real-time database, some system of identifying which buses are late and then where are the buses. And that's really where the real-time system comes in, and that's in protobuf. And you can really easily deserialize that as well with another crate. And so the maintainers of those two libraries, I want to thank them because they make the world for me. But yeah, you can just take those those large structures and just throw them into Postgres. It's really easy because if your Postgres structure lines up with your data structure, then you can just really easily transfer things back and forth. And there's already SQLX is a good library for accessing raw data. So if you want Postgres to generate, you want PostGIS to generate some vector tiles, which is a way of encoding, you want like a series of coordinates that represent your data from this point to this point, right? You can query that as raw binary data. If you're querying tables, Diesel is a really good way because you can do typesave.eq. You're not going to have SQL injections. You don't risk that. And it's very easy to do type checking and whatnot. In terms of graphs, you want to store them kind of as large binary data sets. That's really the easiest way to query them. And if you want to look up like a single timetable, then you can just say, oh, I want to join this table with this table. And Diesel makes that very easy. And as long as you set up the indexes correctly, you shouldn't have a problem. Fun fact, this entire project runs off of a couple Intel NUCs from 9 years ago. So if you can get performance good on one of those computers, you can get if I can get this performance good, then you can hopefully get the performance good on your system as well. So in terms of real-time database, we actually have to query, I think it's about 800 agencies right now. And we have to ask them every single second and say, give me your entire data dump. And unfortunately, the standard doesn't support a way for querying little bits at a time or checking what's different. You just have to query the entire thing. And you can't say, there's no git diff, essentially, for this data. So it's about 10 terabytes a day if you were to do the entire world. So we take all that data, and for a lot of systems are actually proprietary. And that's what we ran into them like dozens and dozens of times. But Rust makes it really easy, because as long as you make some struct that matches your JSON, then you can just convert that struct over. And so you can actually we pop in one for Chicago, one for Via Rail, one for Amtrak. So proprietary systems are quite easily added to whatever system that we have. But it's not really useful. That data's, you have a Unix timestamp and you have maybe a trip ID, but it's not useful to the user just like that. You have to combine it with the schedule. And the schedule contains the human readable elements as well as the actual timetable. And so what we do is we just pull out the database again, line those two up, and then see what the delay is. And we can put that on the map, or we can do all sorts of stuff. Look up the head sign, different elements. Is this wheelchair accessible? Is this not? And then we also have a pool of HTTP servers. And we use Actix. Actix Web is a fantastic library for HTML, and we can just, or HTTP requests, and we can just query which node has the data from etcd. And then from etcd, once we know which node has the data, we just query that node, that server, and say, I want this data, and then our internal server will pass that back and forth. So have an API gateway. API gateway is also very easy to work with in Rust. So the current algorithm that Google uses is based on an algorithm written by Hannah Bass, who's a professor at Universität Freiburg. And it's based on a system of transfer patterns. Instead of looking at a time-expanded graph where you represent every station plus the time, you can instead pre-compute the network as a set of optimal transfers. And so what we do is say, OK, instead of storing every single permutation of every single time, we can split up the station list and split up the arrival list separately. And that's described in the paper. And we've added a little small optimization on top of that to improve the space complexity. But ultimately, the bulk of it is from this paper, but it's not well explained. So we actually had to spend a huge amount of time. Chelsea's sitting in the audience somewhere, and she helped me understand this, and we're writing it currently. But writing data structures in Rust is actually really useful like this as a graph, right? If you can just represent it as a hash map, right, you can just say this node goes to this node, and then you can store the data in your hash map. And if the data is very easily processable, multi-threaded on Rust as well, because there's crates like Rayon, and then you can use Tokyo to assign tasks and whatnot, and just use filters and maps to process the data. So we don't actually output the whole list. We output, say, the transfer pattern is London, Paris, Brussels. So what we actually do is that there's pointers. We instead use RC or ARC, arc pointers, from each station to each station, so that we don't have to copy every single station. That's a memory-safe way of making a graph, is you can just copy RC pointers, those references, and those are very, very, very nice to use in Rust. Most of these implementations are usually written in Java or C++. I find that our code base is actually a little bit smaller than theirs. So that's kind of, if you're developing graph algorithms, I would really recommend, if you're picking something up, try Rust out. It makes it really easy. You don't have to change every single part of your implementation. Like if you had a series of classes, instead you can just modify one struct, and it's not going to affect the rest of the structs. And you can also have like shared implementations through impl blocks. All right, so this is kind of how we do our compression. So usually you would store the entire thing, right? You would store your itinerary list, so your possible list of stations, and then you would store the entire timetable. But it's actually, what we notice is that a lot of them are repeating. They don't change that much. Sometimes the interval does change. And the interval does change for, let's say you have a bus service that they know that at this time there's more congestion, so they'll add more time in between the stops. But usually we're able to get a compression ratio between 3 and 10. The average is about 6 across the whole data set. So from the global scheduled database would be about 600 gigabytes. We can cut that down to 100 gigabytes, and that's much faster to search across on the disk. So let's say you want to say, when will I get to station B from this trip? You can say trip to get the start time, and then just add it. So very simple linear algebra. And so that can be applied to Hannah Bass transfer patterns algorithm, where you can, instead of storing the whole stop list, you store this really compressed thing, and then you can easily fetch it at query time and say, these are all the itineraries, and then it's really fast for the graph algorithm to process through that. So preprocessing OSM. OpenStreetMap is a great resource if you're trying to do anything map-related. And there's actually a download server called GeoFabric, which makes like extracts out of OSM. So let's say you want only this one region. Oh, I want only Quebec. I want only Nova Scotia. I want only Ile-de-France. So you can just query that section out and download it. And then it's a protobuf file. And then there's also a Rust library called OSMPBF that we use to deserialize it. And then you can just pop it into your vectors or whatever. They are very large files, but they're very easily filterable. They have little keys that say, oh, this road is a highway, is a motorway. This road is a footpath. This is a cycle lane. And then there's also restaurants and whatever. You can put them in data structures like R trees, or you can use the R* crate to make those in Rust. But we query out OSM data, and we can crop it into regions, and then even those regions are super big. Maybe they're 500 megabytes. But you're not going to run a query. Let's say I just want to get a class. I'm not going to download the entire province of Quebec into to process. I'm just going to take the little chunk of Montreal and process that. And so we can do that with k-means clustering. Just figure out where the groups of the stations are, and then store those partitions. And then you also want to store the boundaries of those partitions. So, and the same thing applies to the transfer patterns. You don't have to store the entire graph. We can instead store just small little sections of the public transport network. Once we know those border stations, it's much faster to run the transfer patterns queries, pre-compute all the optimal queries from those transfer border stations, and then you have some shortcuts that tell you to go from this border station to the other border station. And so at query time, then you can kind of identify, oh, these are the likely boundaries that I will need to use. You can just query out those and then do a hash map join or a vector join. And that will make it really easy to minimize the amount of memory that you're using and increase the speed of your search. Another thing that you have to do is prioritize making sure that all the costs inside are optimal. And that's what you can accomplish with k-means clustering. So here's an excerpt out of Hannah Bass's paper. I find this really interesting, how there's a minimum amount of border stations, and you can just go to, instead of going through every single possible iteration, you can just hop from border station to border station. So let's say you want to make a cross-country trip, right, from Berlin to Hamburg. You don't have to go through every single permutation. Instead, there's already a shortcut built in. That's the purpose of transfer patterns, that there's a shortcut built in to tell you to get there much faster than if you were to individually query each one, right? So kind of what have we done and what are we doing? We've worked with a number of agencies in the LA area, as well as Washington State. And one of the key things about data science is I realized that Rust is a pretty good language to do for data science. I mean, we typically think of Python or R as good data science languages. But for public transportation data, the data is so complex and so big. Buzzword, big data. This is literally big data. Right? And so if an agency wants to answer a question like, oh, which section of the bus lines are delayed, right? You're not going to run that in Python, and you want to be able to spread out that task. And so these kind of strategies are really effective in not only public transportation, but transportation problems in general. And kind of what we want to continue working on is see what kind of insights we can not only bring to customers, that are looking at what the bus number is, or what direction or what speed the bus is in, that kind of information that we provide that you don't get on the locally made app here or Google Maps, right? Another thing that we want to do is support people with disabilities, people in wheelchairs. And that's really important. Public transportation is often a lifeline for people with disabilities. And it's not sustainable for everyone to be using a car. And so we'd like to say, okay, if you have a wheelchair, can we prioritize these stations are wheelchair friendly, these buses are wheelchair friendly? Can we adapt the query around that? As well as, if you have a bike, and some people, people have different biking speeds, right? My friend or my grandma might have a different speed than me. And so what if we could change like the average speed, or how good am I at doing a little uphill? Am I more comfortable with that? Am I more comfortable going a further distance on my bike? So it's a lot of different choices. And then another thing that people often talk about is often the queries are on other apps are it's only one trip. It doesn't show you, oh, if I accidentally missed this trip, how likely is this trip to happen again? So people want a more stable route to take rather than just a one-off. And so you can also add those factors in. And so with Rust structs, you can just say, oh, I want to add this feature. I want to add this feature. And you just add it as another field inside your node, inside your hash map. Another thing that we were working on is organizing the lines. Often you'll see those really nice metro lines that are drawn. You'll have the lines that overlap neatly on top of each other. And that's based on, from the same university, Dr. Patrick Brosi. He line optimization. That's a really just a comfort thing, but it makes things, if you're looking at a really complex network, if you can see those lines really clearly, that's more important. And then obviously, we'll want to expand our server capacity. Running off a bunch of Intel NUCs is not sustainable forever, but it's a good optimization technique, actually. If you have a bunch of weaker computers, it can really force your team to prioritize optimization off of then just... I wouldn't have done all these optimization techniques if I didn't have a really weak computer. If I had a really... if I have a huge amount of computers available to me, I would just do whatever, right? But yeah, that has been catenary maps. Yeah.